Today, the world has 3 mega skyscrapers reaching over 600 meters, physical representations of man's eternal desire to conquer the sky. From the Tower of Babel to the Burj Khalifa in Dubai, the creation of high-rise constructions has been unceasing. Richard Taillé is a physicist. He went around the world to research the subject, asking the expertise of engineers and scientists driven by their desire to reach for the sky. How were the Egyptians able to build pyramids that dominated the world for nearly 4 millennia? What were the methods of cathedral builders? How did engineers make use of scientific models to design emblematic monuments? Richard Taillé takes us on a vertical journey in the footsteps of those who set out to conquer the sky. To understand how over the centuries men have been able to defy and then master the laws of physics as they build higher and higher. His investigation of man's race for elevation took Richard Taillé to Egypt. At the edge of Cairo, on the Giza Plateau, stand the pyramids. The Pyramid of Khufu, the largest, remained the tallest structure in the world for nearly 4 millennia. What expertise was available to the Egyptians when they built these monuments? It's a mystery that continues to fascinate scientists and Egyptologists such as Pierre Taillé. With him, Richard Taillé visited the pyramids, the last remaining monument of the 7 wonders of the world.
Hello, Mr. Taillé.
Hello.
So, thank you for meeting me here to help me understand the pyramids. It's my first time seeing them in real life. Can you tell me a little bit more about what we see here?
These are the 3 pyramids of Giza, the most famous pyramids. They're in chronological order: the Pyramid of Khufu, which is the farthest, then Khafre, and finally the last one, which is much smaller, Menkor. They were built around 2500 BC.
And how tall is the tallest?
The tallest, Khufu, is over 146 meters high, a height never reached by any subsequent pyramid.
What's really amazing is its steep slope. It must be a 45-degree angle.
The Khufu has a 51-degree slope, with a base of 230 meters, so it's very steep.
And we're a little bit far away, but even from here, I can see that the blocks are huge. How did they move them? Do we know?
The question of the physical construction of these pyramids remains open for debate. Archaeologists believe there were different models of ramps that would have allowed the blocks to be transported. These ramps were used with sleds, so an inclined plane was used to raise the blocks. They're heavy, 2.5 tons on average.
Really?
And it is estimated that for the largest of these pyramids, Khufu, it would have taken about 2.3 million blocks to build the whole monument.
Shall we take a closer look?
Of course.
When observing the pyramids all in a row, a striking detail appears. Their slopes are parallel. This is obviously not an accident, but a mathematical concept, proportion. A case study examined by the historian of science, Evelyne Barbin.
On certain sites, it's very easy to see that all the pyramids have the same slope. You can see this just by noticing that the edges are parallel. So it means that it was planned. And we know how, based on the idea of proportionality. Thanks to the Rhind papyrus, we understand how the Egyptians were able to build the pyramids so that their slopes were identical. We know that the Egyptians had the idea of proportion and used a small triangle. Using that small triangle told them where to place the next stone. The small triangle and the pyramid were similar triangles, as we say today. And this similarity is found in all of the pyramid slopes.
How can we not wonder what methods were used to build these colossal stone constructions?
From the foot of the pyramid, we can really see the blocks. I mean, they're huge. People have an image in their head of armies of slaves working on the pyramids. Is this impression correct?
Not really. Certain films have popularized the idea of slave people working on pyramids. Nothing is further from reality. The more documents we find, the more we realize that the work was remarkably well organized by the Egyptian monarchy, and that the workers were craftsmen chosen by the king. They were well fed, well paid, and employed on a yearly basis for their skills. And according to the American archaeologist Mark Lenner, since it took 2.3 million blocks to build the Pyramid of Khufu, we can estimate that they made an average of 350 blocks a day over the 27 years of Khufu's reign. A team of 800 men is capable, over such a long period, 27 years, of carving all the blocks that made up the pyramid. By making these extrapolations, we've concluded that a team of about 5,000 at the most would have been perfectly sufficient to construct the entire building.
Okay, that's still quite a large team.
The pyramids dominated the world until the Middle Ages. But it was on another continent, in Europe, that the symbolic 150-meter bar would be crossed when church bell towers began reaching for the sky. Around the year 1000, Christianity's development led to an architectural movement with Romanesque art. The desire for height was as much the expression of faith as a show of power. But the race toward the skies advanced with the appearance of the Gothic style with its broken arches. In less than 2 centuries, more than 80 cathedrals were built in France. What challenges did the cathedral builders face? What were their methods? To find out, Richard Taillé went to Notre-Dame d'Amiens, a remarkable structure in many respects, with the greatest interior volume of any French cathedral.
Hello, Richard.
Arnaud, nice to meet you.
So, you're a medievalist, historian, engineer?
That's right.
I don't know if after all these years you're still as awestruck as I am, but I find it amazing.
It never fails to impress. Each time you look, you always discover a detail you've never noticed. So they started construction around 1220. They began erecting a huge foundation of over 7 meters high. It covers the whole surface under our feet, and then the nave was built very quickly.
All right.
Advanced techniques were used to achieve this, especially the advances brought about by medieval industry with serialization, a sort of assembly line approach.
And you don't necessarily realize when you're inside, but it's tall. How high is it?
About 42.3 meters.
So 15 floors?
Yes.
Notre-Dame d'Amiens was a wildly ambitious project, unrivaled at the time. One that holds great fascination for Richard Taillé.
As a physicist, when I see the columns, the mass that is above us, I try to reason in terms of force and mechanics. But I imagine that in the 13th century, these notions were not very well known. Exactly what kind of theoretical tools did they have at the time for constructing these cathedrals?
In terms of theoretical tools, they didn't have much. Mastery of the compass, the set square, the ruler, very good drafting methods, and the right materials. They used the right stone in the right place.
Empirically?
Very empirically. Just by weighing a stone, they knew its density. And they put the heaviest stones on the bottom, the lighter ones on the top. When we make sophisticated calculations today, we realize that these structures are oversized from today's viewpoint because they didn't calculate the size at all. But pillars like this could bear maybe 20 or 30 times the load they currently carry.
Few or no theoretical tools. As for the construction tools like the plumb line or the arithmetic rope, they remain astonishingly simple in light of the scale and the complexity of these stone constructions.
Well, let's try one of these so-called rudimentary tools. We're going to make a right angle with this rope that has
13 knots.
13 knots. We're going to make a triangle with one side, that's 3 units, 1, 2, 3. 4 units here, 1, 2, 3, 4. So if we calculate this on paper using geometry, a triangle with these proportions should have a right angle here.
It's the Pythagorean theorem, but the medieval constructors didn't know this theorem. However, they knew that when a triangle has one side that's 3 units, another 4, and another 5, it's a straight line.
So that gives us a right angle. And it can also help to make horizontal lines. If the vertical line here is aligned with this side, it means that the bottom is horizontal.
Yes.
Let's try. I'm a little intimidated. It's my first time using this medieval tool. Here we go. I'm putting it on the surface. And yes, it's horizontal.
It's remarkable.
So I tested the horizontality of this part of the cathedral. The builders did a good job. We can see that they managed to build something massive and durable using a relatively simple tool.
And that 800 years later, with maintenance, it has remained sound.
But not all cathedrals have been so lucky. A few kilometers away, Saint-Pierre-de-Beauvais has had a turbulent history. It should have been the highest cathedral in the world, but the builders' plans were foiled by the laws of physics, leaving it unfinished. Jean-Lucien Guenon is the heritage officer who watches over it today.
So we're entering the cathedral at what should have been the main entrance if the nave had been built. And we can see the size of the aisle and the choir with its Gothic architecture in front of us. The Bishop of Beauvais, who decided to rebuild the cathedral in 1225, wanted it to be the most magnificent, tallest, and largest cathedral in Christendom. So the vault is 48 meters 50 high, the tallest vault ever built.
At the time, Saint-Pierre-de-Beauvais benefited from advanced technology. It was reinforced with iron. Its arches were supported and bound together with metal tie rods, but this precaution would prove insufficient.
The choir suffered some unforeseen events. It was completed in 1270.
50 years of construction.
And in 1284, some external flying buttresses broke, causing certain arches to fall. It didn't completely collapse, but nevertheless, as a precaution, the reconstruction included a new column in each span.
And that's why it's a very small space.
So 3 new columns were added, in between the 13th century columns.
All right.
Each arch is therefore divided in 2 and supported by an additional column.
We're going to see the upper parts of the church now and look at the tie rods more closely.
Ah, the stairs are very steep.
Here we are.
Okay.
We have a good view here of the cathedral's 13th century architecture and the differences between the original structure and the reconstruction that took place in the 14th century. So we can see this buttress column that is very streamlined, but has a large surface area for the wind. And then a column here in a cruciform shape that's a little less wide but offers protection in this direction. It's really reinforced in all directions.
So more solid, less wind vulnerability, more stable.
Yes, more stable. And if we move forward, we see the structure of the tie rods.
They're iron bars that crisscross.
They're iron bars that connect everything so that the structure is held together if there's movement.
Okay, it keeps everything in place.
The continuity of the chain is the important thing. One wouldn't be enough.
The evolution of Gothic architecture, with its unprecedented successes and spectacular catastrophes, is studied in many universities, including the United States. Richard Taille headed to New York. He went to meet with researchers from Columbia University who are studying French cathedrals using modern scientific tools and have created an index of all of them. Stephen Murray and Rory O'Neill have developed digital tools to better understand Gothic architecture, first off with a huge database called Mapping Gothic.
What's particularly interesting is here that it's arranged by nave height, but we can also arrange by approximate construction start. So here,
Okay, this shows the height.
So here we are in the year 1000. One can look at the heights of building changing, and you don't see a huge amount of difference in them. The great breakthrough of all the cathedrals is Notre-Dame de Paris, and it was the first building in Northern Europe that goes beyond 100 feet in height. Amiens, 1220, and here comes Beauvais, 1225.
Why did it happen at that particular moment?
I would suggest the answer is not simple. And what you're dealing with is a period when the clergy, the bishop, are receiving huge amounts of money from agrarian production and industrial production in the cities and mercantile exchange. So to make a building very tall like Amiens or Beauvais, so in other words, the technology was possible only because they had the resources to do it.
To experience in real time the challenges of the cathedral builders, Rory O'Neill developed a digital simulation, a sort of scientific construction game.
Yeah, the relevance here is to build an appreciation, an intuitive sense of what the builders were challenged with. They wouldn't be sure of how the blocks would behave until they put them up there. And so we can put them up there more quickly in this simulation because each block is behaving as it would. So we have the ability to vary the sizes of the blocks and their configuration in real time. As we try to make this structure taller, we've got the same outward force with this trying to fall and pushing these out, but because these are taller, it's got more leverage to push these things apart.
Okay.
And so height, the quest for height here, is limited to some extent by the ability to vault the space. So what we can do is certainly add more support on the sides, more buttressing.
This holds?
And this holds.
Okay.
But this is expensive. Here we've got a lot more stone has to be quarried. It has to be brought.
Too.
Well, somewhere in Islamic builders came upon the idea of breaking the arch.
A broken arch, an arc brisé.
Arc brisé, d'accord.
And whether or not this was done for aesthetic reasons or structural reasons, we don't know. However, it does help.
Yeah, it works.
Because it's bringing the load more directly to the ground. And certainly, because of the structural benefits, we can start going a little higher and try to make this taller and taller. At some point, this will also fail. So everybody stand back. So here we've got a failure of the structure in static loading. But as we get larger to hold more congregants, a growing city, we need to come up with some other solution here, what we know as flying buttresses. So I think maybe even you could give it a try.
OK, let's go.
Okay.
It's Richard's turn to try his hand at cathedral building and to experience the humbling challenges of the quest for height.
Et avec moi, je vous
I don't want to brag, but mine's holding.
Oh là.
Ah,
J'ai
OK.
parlé un peu trop
I
vite.
spoke too quickly.
Celle-là, elle tient pas très
It didn't last very long.
bien.
Even seismic engineers today are still learning from these masonry structures because their simulations are not as accurate as the buildings themselves. So for the most part, seismic engineers are looking at these medieval masonry buildings to learn how to build better today.
For several centuries, the race for height remained the domain of the sacred. The highest cathedrals in the world, Ulm at 161 meters and Cologne at 157 meters, both in Germany, would only be completed in the 19th century. At the beginning of the Industrial Revolution, the concept of technical prowess surpassed that of religious will, giving new momentum to the conquest for the sky. The engineers performed what were miracles for that time, exploiting new materials. The steel industry was rapidly developing. First iron and cast iron, then steel, would become the primary metals used in construction. Soon, the first skyscrapers were born, thanks to a tragic incident. In 1871, Chicago was a prosperous city of nearly 1 million inhabitants when what was later called the Great Fire broke out. From October 8th to 10th, flames ravaged the wooden buildings of nearly the entire city. 300 people were killed and 100,000 left homeless. As terrible as it was, the episode paved the way for Chicago's technological revolution. Since wooden buildings were now forbidden, architects turned to new materials, such as metal. And so the first skyscraper was born, the Home Insurance Building, designed by the architect William LeBaron Jenney. He said that his goal was a height to rival the Tower of Babel. But apart from the height, it was the construction technique that was truly innovative. In traditional masonry, the load of the structure is supported by the walls. The more height, the greater the forces that are exerted. Hence the need to build thick walls. For example, a 16-story building in Chicago has walls that are 1.8 meters thick at its base. But thanks to the invention of the metallic structure, buildings were able to become lighter and therefore higher. Traditional masonry was replaced by a skeleton of metal girders with the framework connected by rivets. This supports the weight of the building and allows the entire structure to be lightened considerably. Thanks to this new technique, man would be able to set new records in its conquest of height. There was much new terrain to conquer, and soon a rivalry began in the United States. None of this would have been possible without a crucial invention, the elevator. Elisha Otis, an engineer, made the discovery around 1850.
Here it is, the test tower.
To find out just how revolutionary his methods were, Richard Taillé went to the Otis Research Center in Connecticut,
28th floor.
where he had a historical experience.
Welcome. Bienvenue.
Bonjour, merci. Richard.
I am Rick.
Okay.
You'll need to wear a
Ah.
hard hat,
Okay.
safety glasses.
How do I look?
You wonderful. Très bien.
Bah, je m'attendais pas à
Well, I
voir
didn't expect to see a wooden device like this here.
au milieu de cette grande tour.
So that's actually an elevator.
This is an actual lift. In 1853, elevators were used for freight goods.
Okay.
And if the rope broke, the platform with the goods would fall, damaging the materials being manufactured. Elijah Otis, who was the building engineer, said there has to be a better way. How can we prevent the platform from falling? So if you look here, you can see the spring. That came from a wagon.
Okay, so he took something that already existed, the mechanism that has been used in trains.
Yes. And what he developed was an ability to stop immediately the platform falling down if the rope broke. Would you like to try?
Yeah, let's go.
Here? There you go.
Okay.
So let's raise the platform. Right, so that's pulled these two in.
Okay, here we are.
We say cut the rope. The tension will be released. It'll push the pawls into the ratchets, and we're going to come to an immediate stop.
3, 2, 1. Cut the rope.
Wow. Je l'ai senti dans les genoux. I felt it on the knees.
Yeah, absolutely. So in 1853, when Elijah Otis had his assistant cut the rope, he doffed his hat and said, "All safe, gentlemen, all safe."
4 years after this impressive demonstration, the first passengers would confidently ride in the elevator that Elisha Otis installed in New York. Elevators remain the subject of intense research today, but they have allowed, since their invention, the true conquest of the sky to begin. A bitter competition where science clashes with pride. Five years before the World's Fair, which was to mark the centenary of the French Revolution, Gustave Eiffel and his engineers had the idea for a 300-meter tower that would represent the country's rediscovered power and demonstrate its technical prowess.
Hello, Monsieur Lemoine.
Hello, Richard.
It's nice to meet you.
Likewise.
So you're a specialist of the Iron Lady.
Here's this beautiful tower shining under a blue sky on this clear and sunny day, which brings out its graphic lines, its lightness. The structure is 300 meters high, making it the tallest building in the world when it was built in 1889. It was really a visible marker of the technical and scientific accomplishment of the 19th century.
And how was the Eiffel Tower designed? Was it an idea that came from Eiffel? Or was it a commission made for the exhibition?
The tower was conceived by two engineers, Émile Noguier and Maurice Coquelin, who brought the idea for a 300-meter tower to Eiffel in 1884, based on the bridge columns that the company already knew how to build. This would, of course, be both the highlight of the Universal Exhibition of 1889 and also the great achievement of his career.
So now we're at the square under the columns. We can see that they're leaning inwards. how did it stand up before the first floor was built?
The challenge was to start the tower. They began by building foundations, and then the slanted columns. To hold them up, they just used wooden scaffolds, the same that were used when building cathedrals. They started with 4 columns, and it rose from there. The critical point was reaching the platform area on the first floor. We shouldn't forget that they were assembling sheets of metal pierced with holes, which had to be adjusted precisely before putting in the nails, down to the millimeter. From there, it was a kind of giant meccano that could be gradually assembled. In less than 2 years, the tower was built, to everyone's surprise.
Let's go and take a look from above.
Let's go up.
Here we see the structure really well. A view of a void.
We're in between the second and third floor, about 250 meters high, and we see that there's not much holding the top of the tower. There are open-work girders. In total, the tower weighs 7,500 tons. It's very lightweight for a structure of 300 meters. But it has been strategically designed to withstand the wind. The wind creates pressure, several hundred kilos per square meter, which could topple the tower. So they gave it a slightly curved form, which causes the horizontal force of the wind to combine with the vertical force of the tower's weight, giving a resulting force exactly in the axis of the columns.
So the shape doesn't come from the architect's imagination, but from a mathematical calculation.
The shape comes from mathematics, but that's what gives the tower its visual identity, precisely because it's inspired by scientific studies and not by the classic rules of architectural composition.
Okay.
From June 1889, visitors to the tower could safely reach the top thanks to elevators, a real technical feat at the time.
Here we go,
We're going all the way to the top.
from the second to the third floor. We have an incredible panoramic view from here. For 40 kilometers away, it is stunning.
So in 1889, Parisians could come here and see the very same view.
For the first time, they had the chance to go up 300 meters in the sky, and it was a real novelty. And it wasn't just a small group of people who came, but 2 million people.
And they weren't afraid to climb to the top of this great iron tower?
It was a very unusual opportunity. They weren't familiar with mountains or altitude. A lot of people must have had vertigo, but it was also perhaps a way of warding off their fear, saying to themselves, I'm 300 meters high and I'm safe on this small platform. It showed that one believed in the idea of progress, which was strongly valued at the time by all of the citizens.
In any case, I feel safe on this platform. No problem. I'm not afraid of falling.
On the other side of the Atlantic, with a dream of becoming the capital of the Western world, New York began its own race for height. It started in 1894 with the Manhattan Life Insurance Building at 100 meters high. The first real New York skyscraper in a long series that continues to this day. What trials did the engineers overcome to erect these buildings? What new techniques did they use? Richard Taillé explored New York along with historian Mosette Broderick and stopped at one of the city's iconic landmarks, the Flatiron Building.
It's a very unusual shape. It's a triangle. It's where the bedrock of Broadway meets the fashion of Fifth Avenue. And because of its funny location, it got to be known as the Flatiron Building. So it's a building that comes to a point like a lady's iron, although we might call it a piece of cake.
Yeah.
A very tall piece of cake.
But I guess it's not a piece of cake to build.
No. That was a nightmare for engineers to work on. The problem they had was the site, trying to get the flanges to work on this narrow corner. But this is a skeleton steel construction with terracotta fireproof design and cladding. So this is a full skyscraper. It has all the characteristics that are needed to make what we come to call, after the 1880s, a full skyscraper.
From the early 20th century, every bank, newspaper, and insurance company wanted its own skyscraper. It was a way of gaining exposure for their brand and asserting their reputation with a powerful symbol. Buildings of greater and greater heights sprung from the ground until one of them came to dominate the world for quite some time.
We're on Fifth Avenue, 34th Street is here, and right up there is the Empire State Building, the projected world tallest building for many decades. Wow, what a beautiful lobby.
And what about this picture here?
Now, this is wonderful. A big image of the building itself. There it is. A building that sets back under the zoning law of 1916 in a very dramatic fashion. In 1916, after 20 years of people arguing about how big these buildings are, New York City passed a zoning law which basically says that the building starts with a base, sets back at a certain mathematical formula, goes up, and allows people to still be bathed in light and not feel that they're down in an elevator shaft.
The Empire State Building, with its distinctive silhouette, is the ultimate model of the 1916 law. And it was built at the frantic pace of 4.5 floors per week.
It was a construction nightmare. And you know, it involved riveting huge girders in the middle of the sky, looking out on nothing. Now, I don't know whether you've ever seen the...
Oh, pictures of the construction workers.
The thought of it terrifies me. But the special people who do it are Mohawk Indians from Canada, and they were able to get out on those girders and do it. And this building was finished in 18 months. It was finished May 1st, the traditional moving day in New York City. The building was ready on May Day. 1931, the building flopped.
That initial commercial failure did not, however, prevent the 381-meter-high Empire State Building from remaining the tallest skyscraper in the world for 4 decades. One of the defining features of the Empire State Building is that it is mainly constructed from concrete, a 19th century innovation that gradually came to replace brick and terracotta. This material made it possible to reach heights that were unimaginable even a few years prior. Along with steel, concrete remains the primary material used in the construction of high-rise buildings today. The higher a tower rises, the more it is subject to external forces, compression, traction, bending, twisting, and shearing, exerted mostly by the weight of the structure on itself or by winds exceeding 200 kilometers per hour. When subject to pressures that are too great, towers can bend to one side, swinging back and forth, twist in on themselves, and end up collapsing. So they have to be constructed with materials that can absorb these movements. When used alone, concrete has considerable compression strength, but its tensile strength is low. Steel is very resistant to traction and compression. Its physical and mechanical characteristics are the same in all directions. It twists elastically until it breaks, predictably, always under the same conditions. Manufacturers had the idea of adding reinforcements to concrete in order to give it flexion strength, so the tensile forces would be carried by the framework. Thus, reinforced concrete was born. To make it, concrete is poured directly into molds containing steel bars. The latter support the concrete and allow it to effectively withstand the forces that act upon it. Thanks to the advances made in the strength of concrete and also lighter materials and increasingly efficient engineering, the race for height gained new momentum in the 60s. The United States popularized the skyscraper, but the records they set were soon surpassed by Asia and the Middle East. In Asia, Shanghai, Singapore, Taiwan, and Kuala Lumpur, new high-rises were erected each day, with Hong Kong holding the record with over 1,250 skyscrapers. New records were constantly being set. The number of skyscrapers grew exponentially.
It took 135 years to develop 50 super tall buildings. And super tall we define as 300 meters or above. And then the next 50 super tall buildings happened in less than a decade. So the pace of development is absolutely rapid and massive. However, we were seeing such extremes of height that super tall no longer caught the essence of the extreme heights that we were seeing being proposed. So that's why we introduced the term megatall, which is 600 meters and above. And right now there are 3 megatall buildings complete around the world.
The final step of his investigation led Richard Taillé to Dubai. Here he visited the tallest building ever made by man, the Burj Khalifa. "828 meters of concrete, steel, and glass, built in just 6 years. What scientific model did the engineers use to design this emblematic monument, this showcase of modern science? Richard Taillé received special permission to witness the internal workings of the skyscraper, to discover its secrets.
Hello, Mr. Naguib. I'm very pleased to meet you and I have a lot of questions for you. Obviously, in such a large structure, I'd imagine that the elevators must play a very important role.
Definitely, Richard. We have elevator, which is the highest travel in the world, 504 meter traveling. Okay. So let's have this great, unique experience traveling at 10 meters per second. Okay. Please be my guest. This is a double deck. So double deck elevator is like 2 cabins on top of each other. This is the lower deck and we have the upper deck.
Ah, this one here.
This one here. The lower one here, correct. So we're going to take it up to the 123rd floor.
Okay, 123.
Please.
There are 2 buttons.
Yeah, so now closing button.
123rd floor.
Correct. So we'll be traveling around 442 meters.
I can feel the acceleration now.
Yes, and the total travel takes around a minute until you reach for 442 meters.
D'accord.
I've never gone as high as 123 floors in my life.
Please, on the right hand side. Thank you.
It took less than 1 minute to reach an altitude of 460 meters. The highest skyscraper in the world is truly at the forefront of technology. It is permanently under surveillance from an underground control room that Richard Taillé visited.
This is the brain of our building.
The brain, okay, le cerveau.
From here, we get to manage and control and overlook all the operation of our equipment within Burj Khalifa. All the systems that we have in Burj Khalifa are linked to these screens.
power supply, air conditioning, the structure's movements. A close eye is kept on every element to ensure the safety of this vertical city.
I'm especially interested in this one with the small oscillations.
Burj Khalifa is the world's tallest building, and it is acting like a big sail. And we need to always monitor its movement. So what you see here is the actual building movement as we speak now.
As a physicist, I'm interested because I see acceleration marked here. So these are sensors that measure the acceleration of the tower. I imagine you can convert this acceleration into motion, into distance that is traveled beyond the equilibrium position.
Yes, the system has the capability to convert this into millimeters. Currently, although it's a bit windy outside, you can see there is a spikes here, and that is in microns, so it is hardly moving a portion of a millimeter. It is that the building is that stable. Due to wind, the building can tolerate a building movement to approximately 2 meters to any direction.
Building a skyscraper over 800 meters high that can guarantee the comfort and safety of its occupants is a technological achievement. Its designers had to find solutions to problems that up to that point had only been theoretical.
When you're designing these very tall towers, the main load you have to contend with is wind. It's not dead load, which is the weight of the building. It's not live load, which is the load of the people in the building and the furniture they put in.
People don't realize is when wind goes past an object, and if that pulsing matches the natural harmonics of the building, you can get quite large forces. One of our goals of shaping the building was to get the shape which confuses the wind. And the shape of the building, at the bottom, you'll be going into 2 wings, and by the time you get to the top, it morphs into a nose, like the front of a boat. And through this shaping, the wind forces went way, way, way down.
The unique layout of the Burj Khalifa allows it to divert wind. But in structures with more classical shapes, there is another way to resist movement, even from earthquakes. To limit oscillation, these skyscrapers have dampers whose principle is simple. It's a mast that moves mechanically to the frequency of the tower with a certain time delay, thus helping to stabilize the building. There are different kinds of dampers. Some are made from an enormous concrete block which must weigh at least 1/100th the mass of the building, placed at the top of the tower on a layer of oil and connected to the walls by springs. The mass follows the movement of the building, but with a delay due to the oil. In the case of the Comcast Center in Philadelphia, there is a hydraulic damper containing 1,100 tons of water that moves from one reservoir to another thanks to a motion sensor. But one of the most surprising dampers is found at Taipei 101 in Taiwan, a 508-meter-high tower located in a seismic zone. It's a gigantic steel pendulum measuring 5.5 meters in diameter, weighing 660 tons, which can sway up to 1.5 meters, reducing the building's oscillation by 40%. The wind was not the only difficulty the Burj Khalifa had to overcome. With construction projects of this scope, even when they're extremely well thought out, there are always surprises in store. And the most unexpected sprung from an unlikely source, the building's own backers.
The initial design was only 10 meters taller than the world's tallest building at the time, so it was only 518 meters tall. But during the design process, it grew by 310 meters.
The structure was already up at 35 floors. The Emaar management heard that some other developers in the area were going to build another tower that was going to be higher than 700 meters. So everything was kept very quiet, but they instructed us to raise the tower height to 820 meters. So we all came to the conclusion, yes, we can increase it to 820 meters. So the design was changed, and from that period, we went on and finished the tower at 820 meters.
On January 4th, 2010, Dubai revealed a secret that had been fiercely guarded until then, that the Burj Khalifa's final height would be 828 meters. They celebrated the achievement with a spectacular inauguration.
Everybody involved was very proud, and I can say, a large measure of relief. Yeah, it's like, there's a big burden taken off your shoulders. You can say, wow, I can relax now it's finished.
Burj Khalifa is a skyscraper that has beaten all the records. But if it holds the title of highest building in the world for the moment, this will no doubt one day be stolen by another building. Already, the Kingdom Tower, which is expected to reach 1 kilometer, is under construction in Jeddah, Saudi Arabia. And if man strives to reach even greater heights, will there be physical constraints? Insurmountable limits?
The only limit on height, until we get to almost unimaginable heights, like several miles, stratosphere, is financial. There is no technological limit to height. The quest for height means ego and attention. Mankind has this desire to go to the next level, to push the limit. And the quest for the world's tallest building has always been a part of that.
When you go hiking, you want to go to the top of the hill to see what's on the other side, you know? You're walking down the street, you want to see what's around the corner. And so this desire to go high is just, it's somehow, it's in our mythology, it's in our culture. I mean, why go climb a mountain? Well, we do. It's just part of being human.
At the end of his journey through space and time, tracing the footsteps of those who set out to conquer height, Richard Taillé wonders. Since, over the centuries, science and engineering have allowed us to constantly push the boundaries of what's physically possible, will nothing be able to limit man's eternal longing to reach for the sky?